It's a great honor to present at the Conference on Materials Chemistry and Environmental Engineering 2022. My name is Liwei Zhao, and I am a student from Tianjin University of Technology. I appreciate the opportunity to present my paper titled Simulating the Influence of Exhaust Gas Recirculation on Nitrogen Oxides Emission of Diesel Engine with CHENKIN. As you can see, I will introduce my findings in following four areas. First of all, let's look at the background of the study. We first need to understand what is EGR. EGR's full name is Exhaust Gas Recirculation. EGR means that a portion of exhaust gas from combustion of the engine are recirculated into the engine combustion chamber. Secondly, we need to know why EGR is used. According to most past studies, the use of EGR is effectively in reducing the production of nitrogen oxides during in-cylinder combustion of diesel engines. Some academics point out in their research on the mechanism that the use of EGR can reduce the oxygen concentration in the combustion chamber, prolong the combustion duration, and effectively reduce the generation of nitrogen oxides. So we need to use EGR to protect our environment. According to previous studies, there are shortcomings in research aspect, especially the impact of EGR temperature on nitrogen oxides emission. This paper will quantitatively analyze the nitrogen oxides emissions of diesel engines under the EGR conditions of different temperatures and different circulation rates by means of theoretical simulation. Secondly, let's focus on the research methods. We first need to build a combustion model for a diesel engine. To enable simulation, we need to use a suitable simulation tool. The simulation tool I used is closed internal combustion HCCI engine simulator model in CHENKIN to simulate the actual combustion of the engine. In order to find the specific parameters, we need to select a suitable prototype. To simplify it without loss of generator, I choose a 4-stroke single-cylinder non-supercharged 135 diesel engine that has been experimented with in practice. The relevant parameters of prototype are described in detail in this paper. To simplify the calculation, we need to simplify the fuel for diesel engines. It's well known that the composition of diesel engine is very complex, and to simplify the calculations, N-heptane is used as an alternative fuel according to relevant studies. After the model has been built, we need to verify the realism of the model. I compared experimental results with simulation results. As we can see, the red dots represents the experimental results, and the blue line represents the simulation results. Figure 1 shows the variation of temperature in cylinder, and Figure 2 shows the variation of pressure in cylinder compared with experimental results. The trend of the simulation is basically the same as the corresponding crank angle. it shows that actual combustion process in cylinder is similar to the simulated combustion process. The maximum pressure is quite different those in this original experiment. The speculated reasons may be that during experiment, the heat dissipation of the cylinder has deviations from the coefficient set in the model. The actual combustion of diesel engine combustion is different from that inhabitant combustion in the model, and there may be errors in experimental measurements, and so on. I also compare the mole fractions of the main products, such as water and carbon dioxide. The difference in the number of main products generated is less than 5%. The error in these results is within the permissible range. It indicated that the simulation model and its combustion mechanism are in line with actual combustion in the diesel engine. In order to analyze the effect of different temperatures and different circulation rates on nitrogen oxide emissions, the following two experimental schemes are designed with different exhaust gas recirculations, with exhaust gas recirculation rates as variables. In Group A, the exhaust gas is not cooled when mixing with fresh gas. The temperature of the mixed gas in Group A is calculated by conservation of energy. The equation as it follows. In Group B, cooling is performed so that the exhaust gas maintains the same temperature after mixing with fresh gas. Each group has 6 simulated cases with an exhaust gas recirculated rate of 0 to 50%. After running above side of experiment, we obtain the following results. As we can see, the black line represents the results of Group A. The red line represents the results of Group B. Figure 4 shows the nitrogen oxides generation corresponding to different exhaust gas recirculation rates in Group A and Group B, according to the data in Figure 4. In Group A, when the circulation rate is between 0% and 30%, the amount of nitrogen oxides generated increases with the increases of exhaust gas recirculation rate. When the rate is between 30% and 50%, the amount of nitrogen oxide generation decreases with the increase of the circulation rate. But overall, nitrogen oxide generation of Group A remains at a high level. The amount of nitrogen oxides in Group B decreases gradually with increase of exhaust gas circulation rate, and the decreasing trend gradually slowed down. The reason for these results need to be explained in Figure 5. Figure 5 shows the change of maximum combustion chamber in cylinders of the two groups with exhaust gas recirculation rate. It can be clearly see that the in-cylinder temperature of Group A has been maintained between 1,700 and 1,750 K and 1,800 K, and the temperature of Group B gradually decreases with the increase of exhaust gas recirculation rate. According to previous studies, The maximum combustion temperature and oxygen concentration in the cylinder have an important influence on generation of nitrogen oxides, which is mainly generated at about 1800 K. In Group B, the temperature of the mixed gas in each simulation is kept constant by cooling the exhaust gas, and the internal energy in exhaust gas is gradually reduced. The addition of exhaust gas leads to a decrease in proportion of fresh air. It is for this reason that the maximum combustion temperature in cylinder decreases, which also reduces the nitrogen oxide emission diesel engine. Based on the above research, the following conclusion can be drawn. With the same exhaust gas recirculation rate, reducing the exhaust gas temperature can greatly reduce the maximum temperature of in-cylinder combustion, thereby reducing the generation of nitrogen oxides in combustion. Therefore, when use EGR technology to reduce the nitrogen oxide emission of diesel engine, the exhaust gas must fully intercooled in order to achieve the best nitrogen oxide emission reduction. In Group B, with the increase of the exhaust gas recirculation rate, the nitrogen oxide emission of the same amount of fuel in combustion decrease with the increase of the exhaust gas recirculation rate, but the decrease becomes slower with the increase of the exhaust gas recirculation rate. The high exhaust gas recirculation rate significantly reduces the in-cylinder temperature. It is necessary to select appropriate exhaust gas recirculation rate according to actual simulation of diesel engine. Thanks for your listening.